Okay, so welcome. We're going to do a quick exam review for the exam tomorrow. And first thing I would want to mention is that you'd want to have an inventory of the types of problems you will have on the exam. So you should be able to create some sort of, say, flow chart where in your first order differential equation might be separable. And if it's not, you might check that whether it's linear or not, and then know exactly the procedure to use in case it is linear. So you'd want to find an integrating factor and then apply the formula. Okay. Okay. Welcome. What I'm doing is actually going to do a very quick exam review for tomorrow, if that's fine. Okay, so welcome. I'm doing a quick exam review for tomorrow, if that's okay with you. Thank you. All right. So I was saying that you need an inventory of types of problems. So the easiest one is, you can check whether the differential equation is separable. If not, you check whether it's order linear, and you have to be familiar with the procedure of finding an integrating factor and then applying it to get the solution. Okay. And then if it's not first order linear, if instead you have something that it's almost first order linear, but you have this y to the n factor, then of course it's called Bernoulli, in which case you'd want to know the correct change of variable is where we let z or v, whatever your professor called it, be y to the power 1 minus n. And if you do the change of variable correctly, you will get a first order linear differential equation. Okay. If it's not Bernoulli, then maybe it's homogeneous, right? So that's of course where you can write the right-hand side here as a function of not just x and y, but rather a function of the ratio y to x. Okay. In which case you would lump that y over x into a new variable, so another change of variable, and that would turn this into, again, separable. So if it's not homogeneous, perhaps you have a differential equation of the form where y prime is, and you have this ratio, this rational expression where x and y are just simple linear combinations plus a constant. And as long as AD minus BC is not 0, you're doing a shift of variables so that the differential equation does then become homogeneous. Okay, so I should have that should have gone. I should have, I guess, should have gone like this. No, not like that. Sorry, it should have gone like this, homogeneous, right? But then you got to do another change of variable to make it separable. Okay. Now, if AD minus BC does equal 0, then what you have is the right-hand side becomes a function of a combination of x and y up to a constant, in which case you simply lump that into a new variable z, which will turn this into a separable differential equation. Okay, so a lot of times it comes back to being separable. Okay, and then you also learn that if we write the differential equation in this differential form, and the derivative of m, which is the thing that multiplies dx, with respect to y does indeed equal the derivative of n with respect to x. It's exact, and so then we would have to be familiar with how to find a solution of this form where we have some function of x and y equals a constant. So we'll review that procedure. And of course, if it's not exact, then we have to factor, there are some complicated integrating factors, but I would prepare for finding an integrating factor which is just a function of x only. And a necessary condition for that is that this expression is a function of x, or it's a function of y only. And the necessary condition would be that this expression is a function of y only. Okay. So you should be able to create something like that before the test, right? Just run through an inventory of types of problems you'd expect. Okay. So let's just go ahead and do a Bernoulli. Okay. So again, you have this y to the n. So I'm writing this in conventional form, meaning that the coefficient for y prime is 1. So you might have to rearrange a bit to get this in the conventional form. And we know the change variable. Okay. And you should get, if you want to memorize, first order linear differential equation. Okay, so let's just go through an example if you don't mind. Okay. So we have this differential equation. It's not written in the standard form because of this x. So I'm just going to go ahead and divide through by x everywhere. Okay. And if it weren't for this factor, y to the power 5, this would be first order linear. But here it's Bernoulli, so we know that we should do a change of variable where the new variable should be y to the power 1 minus n. Here n is 5. Okay. Now, to do a change of variable in differential equations, you also have to find derivatives. We're going to find the derivative of z. And recall that here the independent variable is x, so we're differentiating with respect to x. So, okay. And then, because y is a function of x, we can't forget that we use chain rule. All right, so now what I would suggest is, since I have a y prime over here and over here, I'm just going to multiply both sides of our differential equation by this factor so as to make the transition, the change of variable easier. So I'm just going to multiply everything by -4 times y to the -5, including the second term. And the right-hand side. And the beautiful thing there is that we have a y to the +5 power, right? And here we have y to the -5. So those will cancel. Okay. So then we see that this term is exactly z prime, right? Y to the -4 is exactly z. Okay. And this is, the right-hand side now is free of z, so it's just a function of the independent variable x. Okay, so that becomes our first order linear differential equation. Okay, so it's already in conventional form because the coefficient for z prime is 1. And identify the function of x multiplying z as -4 over x. Okay. And so what you call the formula for the integrating factor is e to the power, which is the antiderivative of p. So we're going to go get a natural log of x. I'm just going to assume x is positive. Use properties of logarithms, and of course e and log are inverse functions. So it looks like our integrating factor is 1 over x to the power 4. Okay. All right. So the idea with first order linear is that you want to multiply everything by the integrating factor. So multiply both sides by the integrating factor. And if you look at mu, its derivative is designed to be equal to mu because you're differentiating it exponential, so you get it back, times the derivative of exponent, and so differentiating an antiderivative just gives you back p. Okay. So if you do things correctly, mu times p should just be mu prime, and you notice that the left-hand side is just applying. It's the result of the product rule on the integrating factor times times z. Let me erase that. Okay. And so when solving a differential equation, the whole point is to find the unknown function. So all we have to do is deprime the left-hand side by anti-differentiating with respect to the independent variable. And you're going to get a constant of integration that's important on the right-hand side. And so anti-differentiating the derivative, you just get mu times z on the left. And the last step would be to simply divide by the integrating factor. Where you have to remember that the integrating factor has to also divide the constant of integration. So don't forget that. And then you back substitute, right? Z is really like y to some power. Okay, so let's go through that procedure. Just copy this really quickly. Okay. Where did it go? Oh. All right. So we found our integrating factor is 1 over x to the power 4. Multiply both sides. Okay. And without doing too much thinking, we know that the left-hand side is exactly the integrating factor times z, that product differentiated. Okay. Next, we deprime the business by anti-differentiating. Okay, and we get, and on the right, you might, where do students learn how to integrate? Well, differential equations. So that looks like a quick integration by parts. Okay, where if you have a differential integration by parts using with a log in it, we want to make u the log. And dv is whatever remains here. The different and you integrate to find these. So you get 2, -3, -4, So you get 1 over x power 4. Uh, 2. My bad. Okay. And then you're practically done. You get the antiderivative, u times v according to parts. Minus the antiderivative of v du. So okay, so we get plus 1 over x squared. Okay, and then of course don't forget your constant of integration. That's just to isolate z, well not the last step, sorry, and by multiplying both sides here by x to the 4. Okay, and then don't forget that we're not done because z was really equal to y to the negative 4. So z is y over 1 over y to the 4. Okay, and finally reciprocate. So I'm just reciprocating both sides, so that expression on the right goes to the denominator. Okay. And then y would be plus or minus the 4th root of all that business. So that's our general solution. Okay. All right. So that was an example of Bernoulli, okay, where we know for tomorrow what the correct change of variable is, and we know exactly what kind of differential equation we should result first order linear. Okay. So maybe next let's look at a case, well not homogeneous, well let's just look at maybe a shift to homogeneous case. Okay. Or maybe this one, I don't know. Let's see. Yeah, okay, let's do this. All right. So this might look like it's a shift to homogeneous, right? Because you have some kind of linear combination of x and y plus a constant on top and bottom. Okay, but the problem is that if you look at kind of the formula for shift to homogeneous, for us to be able to do that, we need to solve a system of equations where you would have like this matrix of A, B, C, D, and you know that you would have a solution to your system if the determinant of the matrix is not 0, right? But here, this would be, my A would be -2, B is 1. Okay, so the problem here is that if you compute this determinant, you get A times D is 6 minus C times B is 6, so it's 0. So that wouldn't work out. So what does that really mean? It means that we have this situation. The right side is just a simple a function of a simple combination of x and y. And let's see what that would be. So you have y minus 2x here. And if I were to factor over -3 in the denominator, I would get y minus 2x. Okay. So let's highlight that indeed the top and the bottom here are both functions of the expression y minus 2x. Okay. So in that situation, we simply want to lump that expression. Okay. So let me just, we have a situation where the right-hand side is a function of y minus 2x. So the idea is just to lump that. On your practice exam, I think you had something like sine of y minus t or something. So you just let u equal y minus or z, whatever. Okay, and then of course we want to complete the change of variable, so we have to differentiate, and we're differentiating with respect to the independent variable x. So we see that y prime is equivalent to z prime plus 2, so we just do a direct substitution. Okay, so we get z prime is, okay, z plus 4 divided by negative 3z plus 2. And we all recognize that this is indeed a separable differential equation. We can bring all the z business to the right, left, and all the x business to the right. All right, let me just make them smaller. One second, let me see, make sure that's correct. Well, okay, well, it is what it is, so you can separate that. So you have a differential in z on the left and a differential in x on the right. Okay. Did I forget the plus 2? Where's the plus 2? No, I didn't, in fact, right? Ah, okay, yeah, you're right. So, yes, y prime is z prime plus 2. Okay, beautiful. So thank you for catching that. All right. So let's bring the 2 over to the left. And now it's just a matter of doing some, finding a common denominator. So let's see, we get z on top. The 4's cancel. We have a 4 and then minus 2 times 2. So that's nice. Over this common denominator. Okay, so now, thank you, we can bring all the z business to the left. I'm going to leave the 7 on the right, just to, it's easy. It looks nicer. And all right, so then two differentials being equal, we know that the antiderivatives will be equal up to a constant of integration. So I think this is a simple integral. You don't have to do partial fractions for this example. Okay, so we get negative 3z plus 2 times log of z, so log of z squared, say. And really, it's an implicit solution, and we're done after we replace z with the original variable. What was z? Z, we said, was y minus 2x, right? So just go ahead and back substitute. I'm sure I could do stuff like exponentiate to get rid of the log, but I don't think that would be very much nicer. So I'm just going to leave it like this for a general solution. Okay. Yeah, so I guess the lesson there is just be careful of the pitfall. It might look like this is a shift to homogeneous, but this AD minus BC was 0. So in fact, you just have to think of the right-hand side as a function of a combination of x and y. Okay. All right. Let me go back to, let me see if there's something going on in chat. Any questions so far? All right. So, all right. So we did this case. So let's, I guess, move back here and let's look at a shift to homogeneous problem. Okay. So the idea, of course, is that if we didn't have these constants here, right? That's clearly homogeneous because I can divide everything by x, divide everything on top by x, divide everything on bottom by x. And we see that this is really a function of y divided by x. So that would be homogeneous. Okay, but we don't have that situation. We indeed have a plus. So these pesky constants are keeping this from being homogeneous. Okay. So what we're going to do is we're going to simply shift our coordinate system, right? So as to make these constants go away. Okay. So we're going to assume that we can, the original variable is a new variable, say minus some shift h. Okay. And y would be a new variable y bar minus some shift. You can use plus as well. All right. And we're going to choose h and k so as to make the constants go away. Go to 0, right? All right. So to figure out what that is, you're essentially going to be solving this system. But let's see why that is. So let's just directly replace x and y on top. So you get 2x bar minus 2h plus y. So y bar minus k plus 1. Okay. And notice that if I put all the constants together, the idea is to make this go to 0. So that gives you an equation. In fact, it's exactly the one that I wrote over here. Okay. So similarly, do a direct substitution for y and x in the denominator, so you get y, that's y bar minus k, minus x plus 4. So the idea is to get this to be 0. So that gives you an equation where, say, h minus k must be equal to negative 4. Okay, so then you solve that system. So I don't know how, I would just use linear algebra at this point, rewriting the system as a matrix equation. And then maybe using the method of inverse. So I would use the formula for the inverse. 1 over the determinant of the matrix. You exchange the diagonal entries, right? And you change the sign in the off-diagonal entries. Okay, so we get 1 over the determinant. Exchange the diagonals, change the sign of the out diagonal. All right. So we get -4. So we get 3, -9. Okay, so I'm getting that h is -1 and k is 3. Yeah. All right. No stretch. Yeah. All right. Okay. So we have x is x bar plus 1, y is y bar minus 3. Okay. And what's really nice about this is notice the differentials. Dx, if you take the differential both sides, is just dx bar, and dy is just dy bar. So the left-hand side here just becomes dy bar divided by dx bar. And over here, we're going to get 2x bar plus y bar. The whole point of this, if we did this correctly, the whole point of that is the constants would go away, and then you get y bar minus x bar. Okay. So indeed, this is a function of y bar over x bar. Okay. I'm going to divide everything on top by x bar, and everything on bottom by x bar. All right. Okay, so dealing with a homogeneous equation, we know that we simply lump that ratio Okay, so maybe the better way to think of that is that y is equal to z times x, because then it's easy to find the derivative with respect to x. So here z is a function of x, and you have x, so product rule when differentiating. Okay. So over here we can directly substitute on the left, and of course these become z's. So we get z plus x bar z prime on the left, and 2 plus z divided by z minus 1 on the right. So we move this z over, and then combine the two expressions by using a common denominator there. So we get minus z squared plus z plus 2z plus 2. Okay, so at this point we can separate the variables. Maybe I'll leave the negative on the right-hand side. Right, so I just factored out a -1 from here. Okay, so two differentials equal, and tight differentials will be equal up to a constant. Well, you know what? We're not going to spend time using partial fractions here, right? So I'm just going to see if I'll just write down the answer, I think. Oh, how convenient. Okay. So here, if I multiply the top by 2, and let's say the right-hand side by 2, the numerator is exactly the derivative of the denominator. So in fact, we get natural log of z squared minus 2z minus 2. I guess absolute value, technically. Okay. And then here, maybe I would, so this is a good reminder, if I'm going to get rid of the log, I exponentiate. And just be careful that you correctly use properties of exponents on the right-hand side, right? Because e to the power, which is the sum of two terms, becomes a product of those two exponentials. So you'd get e to the c is some arbitrary positive constant. And then, right, so what is z? It's y bar over x bar, so you just got to back substitute. And maybe do some aesthetic things like multiply both sides by x squared. And then, of course, you're not done yet, right? You just got to make sure that since x was x bar plus 1, and then y was y bar minus 3, you got to now back substitute. So let's maybe not waste time doing that. But you do, yeah, you have to replace x bar and y bar in terms of x and y. Okay, so I hope it's fine if I don't complete that. All right, great. So what was next? Okay, so we did the shift to homogeneous, which made it separable. All right, so now we want to review differential equation. Maybe if we rewrite it in differential form, maybe it's exact, and we want to know the procedure for recovering a solution curve. So let's review that quickly. Okay. All right. So we check whether our differential equation is exact. So partial of m with respect to y, take partial of n with respect to x, so those are equal. Then it's an exact differential equation. And so we're going to try to find this function of x and y. And so we can do it either way here. We can take m dx and anti-differentiate it to recover our function psi. But instead of a constant of integration, we get a function of integration, which is a function of the other variable, right? So here the antiderivative was with respect to x. So our function of integration is a function of y, okay, the other variable. Okay. Then we take our results and we're going to differentiate it with respect to y, right? We just finished anti-differentiating with respect to x. We take that result and differentiate with respect to y. And you set that equal to the n, which will allow you to solve for the this function of integration, so to speak. And once you have that, you know your function and your solution, your general solution, is going to be a level curve of that function. And just as a reminder that we didn't have to integrate m with respect to x first, right? We could have actually integrated y. But in that case, our function of integration would be a function of the other variable x. We take our psi and we differentiate with respect to x and set it equal to m. Okay, so let's just do an example. Okay, so m is the business that multiplies dx, and n is this function that multiplies dy. All right, we'll check for exactness, right? So take the derivative of m with respect to y, and then take the derivative of n with respect to x, and then these are equal, so we have an exact differential equation. So now I'm going to recover my function of x and y by, say, anti-differentiating m dx. Okay, so x squared y, and then we get a function of integration, which is a function of the other variable y. Okay. We're going to take the derivative of that with respect to y next. The derivative with respect to y of that. And the derivative of that with respect to y is just phi prime, right? Of course, this is a function of just y, so the prime automatically means a derivative with respect to that variable y. Right? And we set that equal to n. N was right here, yeah. So set that equal to n. All right, and if we do things correctly, anything that has like x's in it should go away. Right, indeed, because we have a function of y, and so of y only, so you better be only left with a function of y on the other side, and of course we just undo the derivative by integrating here. So y to the fourth. Okay, so now we know what our function is. We set it equal to, like from over here, you see was x squared times y plus this function of y, which we recovered here. It's y to the fourth. And a general solution is just a level curve of this function. So you set that equal to a constant. There you go. Okay. Any questions on how to solve an exact differential equation? Okay. So, of course, your differential equation on the exam is going to turn out not to be exact, right? Yeah. So let's just practice trying to find an integrating factor in that case, under the assumption that it's either going to be a function of x or a function of y. There's other types of integrating factors, but I'll just review those two cases. Okay. Integrating factor. Let's see if I have that. All right. So we do the test for exactness, and it fails, right? So it's not exact. So of course the integrating factor is some function of x and y in general, such that if you multiply both sides of your differential equation by u, the integrating factor, the results would be exact, meaning that the partial derivative of mu n with respect to y would be the same as the partial derivative of mu n with respect to x. Okay. And if you use the product rule on this derivative, you just take turns differentiating each factor with respect to y on the left, with respect to x on the right. Okay, and you make some assumptions like we want our integrating factor to be a function of x only, for example. What would happen is that if mu is just a function of x, then this derivative of mu with respect to y would just go away. Yeah? So this term would go away. And you rearrange it, and you get a separable differential equation. And the test is that if this expression is just a function of x, then solving that differential equation would give us this formulaic thing for the integrating factor. Okay, so I don't know if you're allowed notes or not. I don't know how tests work in an online environment. But in the past, I know you had to memorize this, right? That it's a test. If that's a function of x, we know how to find our integrating factor. Okay. On the other hand, if this is a function of y only, then our integrating factor is a function of y, and we find it according to that formula. All right. So maybe you can tell me, do you know, how does your test work? Is it like honor lock or something? Is it it's like a PDF that you download? Okay, well, we'll see. All right, so let's do an example. Oh, it's both. Is there a take-home portion, or is that like there's a both? Okay. Okay, cool. So, did I have an example? Yeah, okay, right there. So let's do an example. My m is the thing multiplying dx. So I guess be careful. Sometimes, there's nothing stopping them from writing something like y squared minus x squared dy, right? And the rest of it. So don't always expect that the dx part comes first and then the dy part. They could easily switch that around. Okay, but m is the thing that multiplies dx. The derivative of m with respect to y is 4xy plus 2x. The derivative of n with respect to x is minus 2x. All right, so those are clearly not equal. So this is not exact. So we will try to find an integrating factor, and I hope that the professors were kind, and then the integrating factor is either a function of x or a function of y. So let's look at these tests here, right? Partial of m with respect to y. So that would be m with respect to y. So this doesn't look promising at all. Minus divide by n. That doesn't look like that would become a function of x or a function of y only. I mean, I can factor stuff in the numerator, but yeah, it wouldn't work, right? So this is not a function of x only. Okay, so I won't be able to find an integrating factor that's just a function of x. So out the window, right? That's okay. I'll try the next case. So partial of n with respect to x minus partial of m with respect to y, all divided by m. So let's see. So minus 2x minus all divided by m. Let's check. Well, there's a little, I think this works out. Just don't be discouraged, right? I can factor a negative 4x in the numerator, sorry. And I can also factor out a 2x in the denominator. And indeed, look, the x's will cancel out. And you have a function of y only. Oh, okay, great. This simplifies even further, right? Okay, beautiful. So we have a function of y only. Okay, so this is a function of y only. We know there's an integrating factor given by the formula, or you can solve the differential equation, e to the power, which is the antiderivative of that expression. Okay. Okay, so it looks like integrating factor is y to the negative 2 power. Okay. All right. We have an integrating factor. So let me just copy the differential equation. And And you know that the job of the integrating factor is to multiply the differential equation. So multiply everything by 1 over y squared. You get 2x. And okay. And I'll just double check. This is like a new m. Let's call it m bar. I'll differentiate it with respect to y. And this is like my new n. Let's call it n bar. Differentiate with respect to x. Oh, with respect to x. Okay. What did I do wrong? What did I do wrong? Oh, I'm sorry, this should be minus. I'm differentiating this with respect to y, so that's like 2xy to the negative 1. So I made a mistake. Okay, so that's good. So differentiating this with respect to x, we get minus 2 over y squared. Okay, I was just checking quickly that in fact we have an exact differential equation. All right. So we're going to find a solution where let's this time maybe integrate n dy, right? So -2. Okay, so we get y minus x plus x squared over y, plus a function. So here we were anti-differentiating with respect to y. So we're going to get a function of integration, which is a function of x only. Okay. All right, so then we take this and then differentiate it with respect to x next. Oops. Of course, the derivative of y with respect to x is 0. We're treating x and y as independent variables, by the way, right? Okay, and we set that equal to the m. Okay, and again, as promised, anything that has a y in it will cancel out. So that indeed phi prime as a function of x is indeed a function of just x. And we integrate in order to quickly find what phi is. Okay. And then, so there we go. We have phi, psi of x and y, sorry, is y plus x squared divided by y plus our function of x, which we discovered is x squared. And a general solution is just a level curve of that function. Okay. Okay, cool. So since we have 15 minutes, I can do another example of finding an integrating factor, or I could very happily answer any questions that you might have before the exam. Any specific particular kind of differential equation you want to go over? All right. So in that case, let's do another differential equation. So let's see, what can we do? Could this possibly be Bernoulli? Anyway, okay, so it's written in differential form. I might as well check whether it's exact or not. Okay, so the derivative of n with respect to y, the derivative of n with respect to x, those are not equal. So it's not exact. Okay. I will see if we can maybe find an integrating that's a function of x only. So if you ever forget, just remember what we're trying to do, trying to multiply m by the integrating factor and n by the integrating factor so that we do get exact. Apply product rule. So this is also, knowing how to do this is also useful if they say, assume the integrating factor is a function, say, of x times y, or something weird, like you just never know. Or maybe on your homework there was a problem where you assumed the integrating factors of functions, say of x squared minus y squared or something like that. So if you get something weird like that, it's always, this is the best starting point for trying to recover, for trying to find an integrating factor. Right. Okay, so we're going to assume that our integrating factor is a function of x only, in which case the partial derivative of the integrating factor with respect to m would be 0. So that goes away. And then notice that I can bring all the terms that have a mu to one side of the equation. Okay, allowing you to factor out mu. And let's just write this derivative of mu with respect to x, and so the derivative of mu with respect to x, let's write it in that way. And then divide by n. And this, so if this is a function of x only, we get a separable differential equation, right? Just dx. This is 1 over mu d mu. Okay, but this needs to be a function of x only, so let's check. The derivative of n with respect to y minus the derivative of n with respect to x, all divided by n. Easy peasy, you get a half, right? So yeah, that can be considered as a function of x only. So solving this differential equation, we get that our integrating factor would be e of the antiderivative of 1/2 dx. Okay, I'm ignoring the constant of integration, of course, because we just need to find some function that works. All right, so the job of the integrating factor then is to multiply both sides of our differential equation. Which will make it now exact. And I will not check this time. I will just trust that we did this right. Okay. All right, so let's assume we did everything correctly and this is exact. What I would probably do in order to recover our function of x and y, psi, I would say integrate this with respect to y, right? That's easier than integrating this with respect to x. That looks like it would you would have to use integration by parts. So it's worth being flexible here, right? So I'm just going to integrate this with respect to y. Giving us a function of x for our function of integration. Differentiating this in turn with respect to x. Okay, we would set that equal to m, the new m's, after the one we get after multiplying by the integrating factor. So that's right here. I'll go ahead and distribute this exponential as well. Okay, indeed, the stuff that has y's in it. So that's it's a good way of saying that you're going in the right direction. So we have only x's left. And so this is a polynomial x squared plus 4x, and I just times this exponential. Yeah, so that is integration by parts. I guess there's no way around it. So I'll just use the tabular method for integration by parts. I'll write down the polynomial that I'll start differentiating until I get 0. And then I have this exponential, which I will start anti-differentiating. Okay, so now we know that the result of integration by parts here it's this kind of tabular method you get by recursively using integration by parts. And let's remember how that works. So it's going to be, it's like u times v, okay, and then we have a minus in the integration by parts formula, so minus, and then we have the next u times v. I don't know how familiar you're with the tabular method. You can always say something in chat. If not, then plus, because remember we're alternating signs, plus the product of the last u times v. Okay. So there we go. So we get x squared plus 4x times my exponential and minus, per formula, 2x plus 4. Yeah, painful, this integration by parts business, and then plus, per formula, 16. Okay. And then you notice that there's an exponential that can be factored out. So let's just, we're going to be left with polynomial times exponential. I'm missing something. Oh, yes, okay, the 16. So it's not too bad. At the end of the day, we have lots of cancellations. All right, so now we know what phi of x is. And then we say, okay, we update psi. Psi we figured out was, where was it? Where is it? I can't even find it. It's right here. So it's 2y squared times my exponential plus this function which we recovered as well. Okay, and so a level set of this function is our general solution. And I didn't do any initial value problems, but you know how to solve for the constant, this arbitrary constant, using an initial value. So for example, they might have given you the initial value, let's say when x is 0, y is 1, right? So of course, this allows us to take this family of curves, which satisfies the differential equation, and simply pluck out the one that works for this initial value. So when x is 0, this is telling us y is 1. So you get x squared plus y squared times e to the x equals c. So apparently the constant is 2. All right. So now we have not a general solution, but a specific particular solution that satisfies the initial value as well. Okay. So you have 5 minutes to ask me any burning last minute questions there, and then we're done. And I'll go ahead and post this on YouTube as well, on the peer tutoring channel. Okay. Do common power questions ever come up on exams? Well, can you tell me what common power question is? Or maybe if you can share a if I let you share a whiteboard, can you perhaps write down an example of what you mean? I mean, add up the powers. Oh, yeah, okay. Geez, I don't know. I know what you're saying. So there's a type of differential equation which is like, it's something like this where it's not quite exact. Okay. I'm sorry, it's not quite homogeneous, right? Because we have x times y, the combined degree of that term is 2. Yeah, x to the 1, y to the 1, taking those powers together. And of course, the degree of the x squared term is 2. So if it weren't for this 1, this would be homogeneous, right? So there is a substitution where we would replace, we could try to make this homogeneous by using the substitution where y is equal z to the alpha. Is this what you're referring to? Yes. Honestly, I don't recall whether that's an exam that's been on an exam before. I'm so far removed, and I've seen so many questions and homeworks that it's like just it's a blur. So I really don't know. But maybe we can go through this. Let's see if this works out, right? Okay, so what's the procedure? Well, of course, as with any change of variable, you want to, let's find the differential dy, because this differential equation is written in a differential form. So dy would be the derivative of z to the alpha, and of course dz. Okay, so then you do the substitution. So you get x times y becomes x times z to the alpha plus 1. dy is replaced with the equivalent differential in terms of dz. And I guess this is just, we leave this alone. Yeah, this wouldn't work out. I just made this on the fly. So, yeah. Right, so here it wouldn't work out because you get x z to the alpha plus alpha dz, right? So the idea is that you want a common degree, so it just wouldn't work out because you'd want 1 plus alpha to be 2 and alpha minus 1 to be 2. So yeah, that doesn't work.